Not calibrated to the oscilloscope, it's just so that we can see what the analog signal looks like coming out of this probe. Now this is measuring the magnetic flux, right, and the magnetic flux density, where the coils that I'm going to show you and how I've got them configured, they are measuring the induced current and voltage. Technically we're just measuring voltage, but depending again on the direction we can tell which way the current is flowing. We don't know how much, but we don't care right now. We're just wanting to look at the signals and how the magnet interacts. So this is picking up the flux density, which is important to note. Okay, and the other ones are picking up the induced voltage and direction. Okay, so now let me show you what the test setup looks like.
Alright, so in this test configuration, I just wanted to show you what the bench looks like. I've got the coils here. I've got a swinging magnet here so we can just check left, right. And then I've also got that all connected to this apparatus. And then I have each channel of the oscilloscope. The first one, which is the yellow, it is connected to the Gauss meter. The blue channel, which is the second one, is connected to the bigger diameter coil. The third channel, which is the pink magenta color, is connected to the smaller diameter coil. And then the last channel, the green one, it is connected to the single strand of wire. The wire is 45, 46 AWG by measurement. I don't know the exact, but it's in that measurement. So the magnet is facing south down, and the coils are configured in that orientation with the Hall sensor. And we are just catching those scope shots as they go by. Stop the magnet so you can see how it's sitting.
Okay, so these are the results from that configuration. And as you can see, they are very interesting results. One thing to note here, okay, is the polarity reversal. All of these are different except for channel 1, because channel 1 is measuring the flux density of the north or the south pole. And they just happen to be the same direction, but everything else is the opposite direction. Okay, so these are again things you need to just pause the video, think about the configuration of how it was set up, and think about what the scope shots look like. Let me get you a closer shot of that setup. Here's a little bit closer shot there of what it looks like. A little closer, you can see, okay, how these dip negative, stronger than each other. They're a similar peak, but they dip stronger in the negative current, going the wrong direction, and it's hard to tell, but there is a little bitty dip on that single wire green trace as well. So let's go ahead and look at what the next configuration is going to look like so that you can guess what might happen.
Okay, now the orientation is as such, and the Hall probe sensor here is actually just like this, so we can get a reading with it. I'll get you a close-up of this because you can actually see the fine wire on there, where before you almost couldn't even see it. Okay, there you can see the really fine wire. It's a really small wire. These are 30 or 45 to 46 AWG by measurement. But you can see how we got that set up. We've got the big coil, small one, and the Hall sensor right in the middle there, holding it by hand.
So the results from that test are here. Now, I don't know what all this noise is. I don't know where that came from, but just ignore it. It's just background noise. I believe it's an AC line from somewhere. It's right at 160 peaks. Well, it hurts. Anyway, so this is what one peak looks like according to that configuration. Okay, and you can see, right, how this goes up, down, and up. Right, just like our coils configured in the very beginning, in the very first test, we had the same result. Now, there's a very interesting thing here that I want to point out that is very critical, okay, and we'll look at that on the last slide. Let me go to the next one. So here's 2 cycles, and as you can see, right, the 2 main coils are going in the same induced direction on each one of these. However, look at the green wire. The single wire showed a directional change according to which way the magnet was swinging, even though it's south facing down. Okay, very counterintuitive. A single wire is showing direction of induced current, but a coil of wire is showing the same direction, no matter which direction it's going, it still reacts the same way. It's very interesting. And again, the Hall sensor is going the same direction. So this is the same test that we just looked at. This is just a closer view of one of the sweeps of the magnet. Now there's a very critical thing to look out here. One of those coils is bigger than the magnet, and one of those coils is smaller than the magnet, than the surface of the magnet. Okay, so let me get the magnet so I can exactly show you what I mean, because I don't want you confused. Okay, here are the two sensors, right? And if you look at the surface area, that coil's smaller than the surface area of the magnet. This one is bigger than the surface area of the magnet. And it yields different results. This is very important. Okay, this is critical to think, all right, what happens on the interaction of that coil to the size of this magnet. Okay, these diagrams are in Newman's book. You can get them, print them out. I will post on here what page they're on in the book. And you can look at the interaction. So why is that important? Do you see how this tries to flatline? This is one passing of one side of the coil. This is the other passing of the other side of the coil. You don't get that here because the coil and the magnet are interacting as one. Here they start to isolate themselves, okay? And that is very important, and we'll get to that at the end of this video. So let's look at the next configuration for the next test. And the last configuration here, it's swinging a bit, but just to give you a visual, it's the same orientation. The magnet is turned, the coils are all the same, and the Hall sensor is like this. So the coil, magnet, and everything else is at a 90 degree. So here is a close-up shot, right? This is the magnet at a 90 degree angle, so it's swinging on its side past the coils, which are standing up. Now, once again, very interesting results. Why is that? Don't forget the yellow trace, and it's kind of hard to see here, but the yellow trace goes down, up, and back down. This is the exact opposite of what we were seeing when the magnet was facing one direction, but it's the exact same as what the coil was showing when it was flipped the other way. You really need to sit down and look at the tests and look at the results, because these are basic fundamental things that Faraday was trying to discover in his time, but he didn't have this kind of equipment to do it, and now we do, and we get to see very clearly the results that are very important to us. So, and also note, okay, what's going on here? The single wire goes up, down, and back up. Okay, again, 4 current reversals here, 3 current reversals on the single wire, and the magnetic Hall sensor actually shows us 3 reversals, because you got to remember the magnet is on its side. So we should see that. So this is a very clear indication of which way the coil acts and which way the magnet acts when they interact with each other at different angles. This is the point of the test. So let's look at a faraway shot and see if these are polarity swapped when the direction goes the other way. And look at that. They are reversed. However, what's interesting to note is the single wire. The single wire is not reversed. The Hall sensor goes up, down, then up. Over here it goes down, up, then down. And you can just go ahead and see the other pink slash purple and the turquoise slash green. Oh, I'm sorry, that is the turquoise. And then you can see the green. Look at the green. Up, down, up, down, up. So these are in the same direction, right? And everything else is in the opposite direction. Again, very important clues to why these make clear indication of understanding. Let's go ahead and move on to the next orientation of the setup. So this is the current configuration. I've got a big coil, a small coil, the Hall probe sensor, and a single wire, all connected into one spot. There you can see the orientation of the magnet. So here is the result of that configuration. So now, look what's happening. The Hall sensor, right, and the induced voltage are acting pretty well the same. See that? And look what happens to the single wire green trace. Let's go ahead and look at a faraway shot and see if the polarity flips. And there you go. And here is a closer shot of what's going on there. You can actually see there's a tiny bit of negative or opposite current flow on the purple one. Not so much on the green one though. Again, all these little bitty tiny observations are very crucial to understanding the real interaction between a coil and a magnet. And if you want to do what I'm doing, you're going to need to really understand this stuff. I'm presenting it to you in the best way I can without getting so deep that you'll get confused. So what I'm highly recommending is just read Newman's book, cut these diagrams out, put two of them together, see how they interact. Then you can understand a little bit more how the coils and the magnets will interact. Come back and watch this video again. Stop at every single one of these slides. Look at the setup. Look at the result and think really hard.